Last time, we talked about different views about an angle. One of such was physical properties of the angle, that if you start with an angle and shift it, there should be no change in the measurement of the angle. We can also talk about starting with an angle and rotating it, and we should expect no change after a rotation as well. Finally, if you start with an angle and change the scale, there should be no change in the measurement after scaling as well. One crucial consequence for this is if you shift along the line, you end up with two different angles that measure the same. Similarly, if you rotate an angle by 180 degrees, you get the same shape despite you only did a 180-degree rotation. So let us set up some vocabulary. A straight angle is an angle that measures 180 degrees, just like what we talked about last time. Supplementary angles are two angles that add up to 180 degrees. So you start with a straight line and it would divide into two angles and they add up to 180 degrees, as just what you see in this picture. Complementary angles are two angles that add up to 90 degrees, whereas the vertical angle, or sometimes called the opposite angle, are two angles formed by intersecting lines that are congruent. We can also talk about vocabularies involving parallel lines. One way to visualize the parallel line is to think of it as a before and after view of the shift. In that sense, if you have a pair of parallel lines, an orange line called the transverse line, I can think of the angle on top as the before the shift, and the one on the bottom as the after the shift. And they naturally correspond to each other because they're on top of the black line and on the right side of the orange transverse line. They're called corresponding angles. Similarly, in this picture, you can spot four pairs of corresponding angles, green one being one such pair. We can also name angles with respect to their position. Between black parallel lines, we will call any angle we see as interior angles. So if two angles are on the same side with respect to the line in the middle, it forms the same side interior angle, depicted in blue in this example. By the same principle, if two angles are in opposite, they're called alternate interior angles, depicted in gray in this example. Now that we have all the vocabulary needed, let's do some math. So we've established that by rotating, the opposite angles, in this case A and C, must be the same, that they are congruent. And also by the same fact, B and D must be congruent as well. But proving something requires more work than simply saying it must be true. One way of proving, while not efficient, is to list all relationships we know and try to produce a chain of reasoning. Let's say I'm interested in proving A is equal to C. We can list all complementary angles. So A and B add up to 180, A and D add up to 180, B and C add up to 180, and C and D add up to 180. Since we like angle A and angle C, we can try to find every statement about A and C. By picking two statements on top, we can form a chain involving A and B and B and C, which forms a chain of A, B, and C, and that ends up proving a statement about A and C. So we can see that A plus B is equal to 180, B plus C is equal to 180. So A is 180 minus B, C is also 180 minus B, which gives you A is equal to C. Now you can actually pick the second statement. So I can pick A plus D being 180, C plus D equals 180, and get another chain that proves A is equal to C as well. We can do something similar for alternate interior angles. Let's say we know corresponding angles are always congruent and would like to show two alternate interior angles are congruent. We can introduce another angle in blue and think of this as an intermediate step. Now compared to blue, one is the opposite angle, whereas the other one is a corresponding angle. These two form a chain because, as you can see, blue is in the middle and it shows the top one corresponds to the bottom one. And we can deduce that they must be equal. Again, this isn't the only way of showing something is true. You can pick some other angles to compare, but it illustrates how forming a chain gives you an actual proof, starting from one of the facts and leading to another. In general, if you have a pair of parallel lines, you get a large list of relationships to work with, starting with complementary to opposite angles, corresponding angles, and alternate same-sided interior angles. In this way, you can see all properties are interlocked. Let's say I'm starting with an alternate angle, D is equal to B prime. If I combine that with C plus D being adding up to 180 degrees, that naturally gives me B prime plus C is equal to 180 by simple substitution. One final question we can ask is, do the relationship hold for two lines not parallel? Let's say we start with two black lines, obviously not parallel, and a transverse line. We can ask things like, do the corresponding angles match? Are they equal? Now, from the physical point of view, this is clearly no. The one physical argument for corresponding angles being the same was that the parallel lines were simply shifts of one another. So this is clearly no. But showing this directly will be very hard. In fact, it's easier to attack with that as a contrapositive. So that is some comment for actually showing why this must be true. So here's a summary. So we talked about vocabulary. So starting from supplementary angles, opposite angles, corresponding angles, alternate interior angles to same-side interior angles. We also talked about the basic proof method called the chain of reasonings, where you list all of the known facts and try to come up with a chain to prove whether something is true or not. And I've demonstrated that this method shows you how concepts are related and interlocked in a way that one implies the other. Thank you for watching the video, and I'll see you next time.